Okay, guys. Boom. Earth energy structure and the rock cycle. You're halfway through the class. You finished your second exam. And now we're making a huge structural shift. So instead of being looking at things from the sun down to the earth, now we're starting from the inside of the earth and working out to the edge. Earth energy structure and the rock cycle. People. Here's our game plan. Where are we going? Geologic timescale, Earth energy from isotopic decay, Earth in cross section, the magnetic field, major rock types, and the rock cycle. Okay, so this is where we're going. The point of this diagram is to intimidate you. But we don't need to worry about it yet. I'm going to be referring to this diagram through several lectures in the future. And you will need to know it for the last exam in this class. But right now we're looking at the rock cycle. We're starting right here. And we haven't learned this stuff yet, so I'm not going to focus on it. So this is just like a preview. Okay, this is cool. This is not a fake image. This is a real image taken by a spacecraft, the Cassini spacecraft, on the backside of Saturn with the sun illuminating the rings of Saturn. And the reason I'm showing you this picture is because that dot right there is Earth. Okay? That tiny little dot. And that little dot reminds me of a really cool quote by Carl Sagan that I'm going to read to you because it should blow your mind. I think it's a fun way to start the back half of the class. So here we go. Look at that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines. Every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust, suspended in a sunbeam. The Earth is a very small stage in a vast cosmic arena. Think of the endless cruelties visited by the inhabitants of one corner of this pixel on the scarcely distinguishable inhabitants of some other corner. How frequent their misunderstandings, how eager they are to kill one another, how fervent their hatreds. Think of the rivers of blood spilled by all those generals and emperors so that, in glory and triumph, they could become the momentary masters of a fraction of a dot. Our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity, in all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world known so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit, yes. Settle, not yet. Like it or not, for the moment, the Earth is where we make our stand. It has been said that astronomy is a humbling and character-building experience. There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world. To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we've ever known. This is the actual picture taken by Carl Sagan with the Voyager 1 spacecraft in 1990. And the tiny little picture, I've kind of made it blue so you can see it better. Otherwise, you wouldn't be able to see how small our planet looks from outside the orbit of the solar system. And he was so impacted by this image of our planet taken from so far away that he wrote a book called A Pale Blue Dot. And that passage I just read to you, I think, is incredibly relevant and is the most famous quoted section of the book. All right, so let's take a look at Earth time. The planet's roughly 4.6 billion years old. It's a big number. It's hard to kind of put into your head. When you work with these numbers all the time, it doesn't really faze you. But that doesn't mean it's not incredible. So a way to think about it is if you compress all of Earth time into 1 year, the dinosaurs would have died off on Christmas Eve of that year. So almost the entirety of the year would have passed. And the humans don't start running around until 8:30 p.m. on New Year's Eve. Okay, so you think of Earth time as it's deep, deep, deep time. This is all of it right here, starting way back in the Archean period, or also known as the Precambrian. You get the formation of the moon when we get hit by a Mars-sized object in our early history. We start getting our first life around I think we found evidence back now, like 3.7 billion years ago. And life stays small and tiny all the way up until the Cambrian explosion right here before the Paleozoic. So between here and here, life is really nothing but algae and tiny little stuff. Although right around here you start getting bigger critters that are eating each other. But at this point, animals start to form bones and shells that preserve a lot better, so we have a much better record. Mesozoic, you get the dinosaurs, and then lastly, the Cenozoic, dinosaurs have died off, and it's the age of mammals. And then obviously the humans are this tiny little sliver up here at the top, okay? Deep, deep time. All right, Earth energy from isotopic decay. So the primary source of energy that we were interested in the first half of the class was the sun. Now we're interested in isotopic decay. So to understand that, we need to talk about the Big Bang stars and supernova that generate all the atoms on our planet, the matter package. Some of that matter, some of these atoms are isotopes. They are matter that's not stable, and that's because they formed in these extreme environments. They change from one element into another element and release energy in the process. They decay, they break down, and pop off energy. It's also known as radioactive decay, and you can use the decay of these elements as radiometric dating. That's how we're able to actually date the age of the planet at 4.6 billion years old. So this is neat. This is actually a really cool example of the Big Bang. The Big Bang, once it happened, initially all we had was matter or atoms up to lithium. So you had hydrogen, helium, and lithium. But after that, because we have gravity, stars started to form, and the early stars would basically make elements. They were like factories through fusion that could get elements from helium all the way up to iron, which I'm pretty sure is 26 on the periodic table, which is a lot. But to get all the way up to the highest on the periodic table, up to plutonium, you need supernovas. You need the explosion of a very, very large stars with extreme energies and pressures to manufacture these large atoms. Okay? Boom! There's a picture of a supernova in process. Boom! Plutonium, uranium, gold is all being made in that thing. Here's a periodic table. Here's iron, 26 on the periodic table. So the Big Bang got us hydrogen, helium, and lithium. So hardly anything. Stars can get us all the way up to iron, 26 on the periodic table, and then everything else only happens all the way up to plutonium. All this stuff's just made in a lab. Only happens through the explosion of stars. But we find all this stuff on our planet, which means our planet is made up of the remnants of stuff from the Big Bang, stuff from stars, and stuff from the explosion of stars. And that should explode your mind. Atoms consist of protons, which are positive, neutrons, which don't have any charge, and they're surrounded by negative electrons, and they spin around. What will happen is isotopes are when unstable atoms decay protons, so those protons break down, they pop off an electron and some radiation in the process, and they form neutrons, okay? And they change the atom. You use this to date rocks. So here's uranium-238, which decays to lead-206. It breaks down eventually to lead-206. It takes 4.5 billion years to do that. Or that's a half-life. That's the time it takes for like 5 grams to decay to where you have 2.5 grams of uranium-238 and 2.5 grams of lead-206. Potassium-40 to argon-40 is 1.3 billion years for the same thing, to where you have half potassium-40, half argon. And carbon-14 to nitrogen-14 is 5,500 years or thereabouts, which is useful. Here's a fire pit near Stonehenge, and the charcoal in this fire pit you can date using the carbon-14 to nitrogen-14 dating method when you look at how much nitrogen-14 has decayed from carbon-14. I don't know. It's cool. But that's the reason why the interior of our planet is hot, is because those elements decay and break down. It powers plate tectonics, earthquakes, and volcanoes. So here's our planet in cross-section. We got an inner core that's solid. It's iron-nickel. We have an outer core liquid, iron-nickel, forms our magnetic field. Mantle, which is solid, and asthenosphere, which is plastic. And plastic means it flows, but hardly at all. And our lithosphere, which is brittle, so it breaks and cracks. So there's our big metal BB in the center of our planet, this giant metal ball. In the middle, our inner core, made up of iron and nickel. And the reason it's made up of iron and nickel is because the iron and nickel that was on our planet is heavy, and gravity forced it into the center. Surrounding it is an outer core made of liquid, iron and nickel. And this stuff is so liquid, it actually flows more than water. Okay, it's has very, very low viscosity. Very, very easy for it to flow. And that outer ocean of metal, as it streams across the inner core, the inner metal BB, it strips off electrons from that inner core, and that's what actually builds our magnetic field surrounding our planet, which is really cool. Outside of that, we have our mantle. Don't worry about upper mantle. The mantle is where you start getting our rocks, but you want to think of these guys like Darth Vader rocks. They're scary, they're dense, they're thick. Not thick's not a good word, but they're dark. And then the asthenosphere is where we're kind of plastic. It flows, but it flows like glass flows, which you don't think of glass flowing like a liquid, but it does. And that's how flowy the asthenosphere is. And then sitting on top of it is our crust, which is very, very thin and very, very brittle. But this is all the light, fluffy rocks. These are the marshmallow type rocks on our planet. Here's the Earth in cross-section again. You can have thick continental crust where you have continents, very thin where you have oceans. In cross-section, it stretches all the way from San Francisco all the way to Halifax, Nova Scotia, if you wanted to go from the surface all the way to the center, which is roughly 2,900 miles. I asked the question down here, how deep do you think we've ever sampled? Well, it turns out the deepest we ever drilled is, I don't even think we've made it to San Francisco. And the deepest rocks we have are from this upper mantle area. You get diamonds. Diamonds are about the deepest rocks we get. And what's fascinating is to get diamonds, diamonds are really pressurized carbon. They have to make it from down here, Yellowstone, all the way to the surface of the Earth in less than a minute. So it's faster than a supersonic jet could fly. Okay, that's how fast the magma has to erupt out of the volcano. Boom! How cool is that? The deepest hole we've ever drilled on our planet is the Kola Super Deep Borehole, 42,000 feet, penetrated 1/3 of the Baltic crust, and it missed the center of the Earth by 2,890 miles. So we've been nowhere near the center of our planet. The ocean's very deep. It's actually 35,800 feet deep, where it's 16,000 pounds per square inch. Okay, very extremely high pressures because all that water above it. Boom! Isn't that cool? I keep saying boom. I gotta stop doing that, but this is just a cool sinkhole picture. Just put it there for fun. You don't want to live there. The reason we know what the interior of the planet looks like is because as earthquake waves go through, you have P waves, which travel longitudinal. They kind of like a slinky, goes compresses, expands, compresses, expands. They travel fast. Then you have S waves that are like wavy, and they travel slower. But they travel, their speeds change when they go through rocks of different density, and Yeah, different density, and it tells us a lot about the inside of our planet. Kind of gives you like a CAT scan of the planet. That's what let us know what the interior is like. Here's just a cool image for how we have a magnetic field. That liquid outer core of iron nickel generates our strong magnetic field. One thing that's cool is the magnetic field doesn't stay put all the time. It kind of wanders about, and then it actually will flip. It'll point south sometimes, and it points north. The best thing about our magnetic field is that it blocks solar wind. This is a really cool image. Solar wind are highly energetic particles that erupt off the sun, and if it wasn't for the magnetic field that deflects all those particles, our planet would be bombarded by these particles, and we'd all be dead. So there. All right, the rock cycle. Let's talk about what is a mineral, what's a rock, the major rock types, igneous, sedimentary, metamorphic, and rock cycle as a whole. You want to write this in your notes. A mineral is more or less an elemental or chemical compound with crystalline structure and formed as a result of geologic processes. A rock is an object that resulted from geologic processes and consists of minerals. Simple version. Minerals are crystals. Crystals can be really cool, big, cool things you buy at rock shows and stuff like that, which I'm sure your house is loaded with. All rocks are made of crystals. Rocks are combinations of crystals. Now, oftentimes when you look at rocks, you're like, you gotta be kidding me. Like you look at rocks, you're like, there's no way there's crystals in this thing. But if you zoom into even like a boring looking rock, this is what it looks like. It is made of crystals of all types of different minerals. Sometimes they get big and beautiful like this, which I would love to have. Yeah, anyway, if you take a thin section of a rock, you can actually go in. This is what a thin section looks like. If you illuminate it, you can clearly see the different minerals. And actually, this is how you determine what type of rock it is, because you can count the types of minerals and how much of the different minerals make up the rock. Okay, igneous intrusive and extrusive. So igneous rocks form from magma, and magma is the hot molten rock that forms on our planet. The reason it's hot and molten is because of isotopic decay, radioactive decay, the heat inside of our planet. And because it's molten, it's less dense, and it can erupt onto the surface, forming volcanoes. Sometimes the major portion of the magma chamber will actually cool in the subsurface, and a big chamber of cooled magma in the subsurface is called a batholith. Igneous extrusive extrudes onto the surface. Igneous intrusive never makes it to the surface, and through erosion gets exposed later. So basalt is a great example of igneous extrusive. It's made up of crystals, but the crystals are going to be small because this magma cools quickly on the surface and doesn't have a whole lot of time to grow. So you have small crystals, igneous extrusive, and this is a cool shot. I would love to get one of those metal spoons and collect this stuff. Take it with me. Baby rock, brand new rock. Rock birthday. This is SP Crater near Flagstaff. There's a recent volcano, and you see the same thing. Here's a flow of magma heading out that direction. This is a cinder cone from when the gases are trying to get out. It's like puh, 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 puh. It spits out all these cinders. All right, igneous intrusive. So magma that cools on the surface has a long time to cool until the crystals get bigger. And an example is granite, and everybody loves granite. It erodes into rounded forms. This is near the McDowell Mountains. This is Joshua Tree. Everybody loves this stuff. I love this stuff. This is cool. This is a picture from the top of Mount Whitney. It's the highest mountain in the continental United States, 14,464. And every rock you see in this picture is made up of granite. But granite forms deep in the earth, right? It's those magma chambers that cool underground. So what had to happen to get this granite up on the surface? You guessed it, erosion. You had to uplift all this rock, erode all the other rock off to have this stuff exposed. And we're talking at least 10 to maybe 50,000 feet of rock have been eroded off. No way. Okay, sedimentary. So once you take magma as a volcano or as those mountains that you saw, you erode it, you break it down. And you'll break it into pieces, which are clastic sedimentary rocks like sandstone, where you have pieces eroded and then they get glued back together. And you can have big stuff together like a conglomerate, down to sand, silt, and finally clay is the tiniest stuff. You can also have chemical sedimentary rocks, and in chemical, you have to dissolve the minerals through water, and then the water undergoes a chemical process where those crystals reprecipitate out of the water, and they collect on the ocean floor or in lakes. And the classic example is limestone. Limestone is made of the same stuff, the white stuff that builds up on your sinks at home. And it's the same thing. Through chemical processes, the limestone that's dissolved in the water gets precipitated out. And you get fossils. This is a lame picture of a fossil, but it's my fossil. I found it. All right, then lastly, you got metamorphic. And metamorphic means you cook them. So once you've made sedimentary rocks, or you have igneous rocks, but they get buried somewhere, like in a delta or in a subduction zone. When you bury rocks, it gets down on the planet where it's hot again, and there's a lot of pressure, so you cook them. So gneiss is an example of granite, but the granite has been cooked, so you can see all the banding that takes place where the quartz crystals align with each other, and it's because it heats up and they melt and they become buddies with each other. That's foliated. That's when you get the banding. You can have non-foliated, and all that means is just they heat up, they cook together, and they get really, really hard. So this is a quartzite. So instead of having sandstone that's made of individual grains, it gets cooked, and all the grain, you can't separate the grains anymore, and it's one solid rock. So it's very, very hard. This is actually the hardest rock in the world. And these are really cool ripple marks from an ocean 1.3 billion years old. Boom. Again. So that's the rock cycle in a nutshell, right? You have igneous, starts it all. Either magma erupts on the surface, igneous extrusive, cools underground, that gets uplifted later, igneous intrusive, erodes, breaks down into sediments, or gets dissolved and reprecipitated as crystals to form limestone, gets compacted into sedimentary rocks, then you cook them, and you form metamorphic rocks, and if you continue cooking, you can go all the way back to magma, and it's a beautiful life cycle. Not life cycle, rock cycle, but you can skip steps. You can go straight from the magma straight to just getting cooked again, so it's obviously doesn't always happen this way. Okay guys, so that's this lecture. We've covered Big Bang supernova stars, responsible for all the elements on the planet, Earth energy from isotopic decay, different layers of the Earth and whether they're solid or liquid / plastic. We've got a spinning inner solid core with a liquid outer core. That makes our magnetic field. You need to know the difference between a mineral and a rock, 3 major rock types, and breakdown within each major rock type. By that I mean, so igneous is a major type, and then the smaller breakdown is extrusive or intrusive. Sedimentary is a major type, then you have chemical and clastic. And then how the 3 major rock types interact to generate the rock cycle. Have a great day. Thanks so much for listening, guys. Have a good one. Bye.